Okay, fundamental theorem of calculus, part 2. Part 1 of the fundamental theorem said that they gave a formula for finding an antiderivative. That formula was sometimes difficult to evaluate, but expressed it in terms of an integral of the original function. This part 2 gives a way of using the antiderivative. If we know the antiderivative, it uses a way of using the antiderivative to evaluate a definite integral. So it basically gives a shortcut for evaluating a definite integral. Fundamental theorem of calculus, part 2, FTC, part 2. If a function f of x is continuous on a closed interval a to b, and if the function is capital F is an antiderivative of little f of x, in other words, f prime of x is equal to little f. So if we know an antiderivative, then we can evaluate the integral. So the definite integral then is integral from a to b f of x dx. It can be evaluated as capital F of b minus capital F of a. So, for example, this function here, we evaluated this before using the definition of a definite integral, and we came out with 28. The area underneath the curve here was 28. If we apply the second fundamental theorem of calculus, this is going to be the antiderivative of this. So we need a function whose derivative is 2x plus 1. So if we reverse the process of taking derivatives of x squared has derivative of derivative of x squared is 2x. So the antiderivative of 2x is x squared. X has derivative 1. So an antiderivative for 1 is going to be x, because the derivative of x is 1. So we want to evaluate x squared plus x at 1 and 5. Okay. If we evaluate at 5, this is going to be 5 squared plus 5, and then we want to subtract off capital F of 1, so it's going to be 1 squared plus 1. 25 plus 5 squared plus 5 is 25 plus 5 is 30. 1 squared plus 1 is going to be 2. 30 minus 2 is 28. So that's the same answer we had before, but we're using an antiderivative to evaluate the definite integral, and it's a shortcut. It's a much shorter process. So we could have used a different antiderivative. So for example, if we had used x squared plus x plus 23, for example, instead of x squared plus x, this has the same derivative. If you take the derivative of x squared plus x plus 23, derivative of x squared is 2x, derivative of x is 1, derivative of 23 is 0. So you still have the same original function. So we could have used this one here if we evaluated x squared plus x plus 23 at 1 and 5. So we're going to have 5 squared plus 5 plus 23. That's f of 5 minus 1 squared plus 1 plus 23. This is going to be 25. 5 squared plus 5 is 25 plus 5 is 30, plus 23 is 53. 23 plus 1 plus 1 is 25. 53 minus 25 is 28. So we could have used a different antiderivative and gotten the same result. It doesn't matter which one we use, but we could, as long as capital F is an antiderivative for the original function, then the definite integral is going to be f of b minus f of a. Okay, so evaluate 2x squared plus 5 from 0 to 2. So we need an antiderivative for 2x squared plus 5. So that's going to be x cubed, because you can check x cubed. X cubed is too big. So that becomes 3x squared. So we need 2x cubed over 3. Let's try that one. So if you can check, you take the derivative, you'll have 3 times 2 times x squared divided by 3. The 3's will cancel. That gives you 2x squared. And then we can do 5x here. And evaluate at 0 and 2. So if we plug in 2, 2 times 2 cubed over 3 plus 5 times 2. And then evaluate at 0. 2 times 0 cubed over 3 plus 5 times 0. So this is going to be 2 cubed is 8. 8 times 2 is 16. 1603 plus 10 minus 0. We get a common denominator. 1603 plus 30 over 3 be 46 over 3. Okay. Antiderivative of square root of x. So we're reversing. So let's write this with an exponent, x to 1/2 power. So so when you're taking the derivative, you subtract the exponent and multiply by the old exponent. So we're going to reverse that process. For the antiderivative, we want to add 1 to the exponent and divide by the new exponent. So this is 1/2 plus 1 is going to be 1.5 or 3/2. And then we want to divide by the new exponent with 3/2. Evaluate at 1 and 4. So this is, if we dividing by 3/2 is the same as multiplying by 2/3. So it's 2/3 x to 3/2. Evaluated at 1 and 4. So you can check if you take the derivative, take 1 away from the exponent. 1 is the same as 2/2. That gives us the old exponent, and multiply by the old exponent. So 3/2 times 2/3 will cancel, and that just gives us x to 1/2. Okay, so this is going to be 2/3. Let's write this in radical form. So the denominator is the root, so it's the square root. The numerator is a regular exponent. So this is going to be 2/3 square root of 4 to the 3rd power minus 2/3 square root of 1 to the 3rd power. Square root of 4 is 2, so it's 2/3 times 2 cubed minus 2/3 times 1. Square root of 1 is 1. 1 cubed is 1. So 2 cubed is 8. 8 times 2 is 16. So it's going to be 16/3 minus 2/3, which would be 14/3. Okay. Okay, a couple more examples. The integral from 0 to h of sine x. Remember that the derivative of the of minus the cosine is going to be the sine. So it's going to be minus the cosine of x from 0 to pi. So we're reversing the process of taking the derivative. So you can check the derivative minus cosine is equal to sine. So this is going to be minus cosine of pi minus a negative cosine of 0. cosine of pi is -1, so this could be minus -1. Cosine of 0 is 1, or minus -1 minus -1, so it's going to be 1 plus 1, which is 2. Yeah, the integral of the sine, let's see, this is 1 minus 1, maybe pi is right here. Remember the graph of the sine function, the equal to 1 at pi over 2. The graph of the sine goes something like this. So the area that we're interested in is this area here. So that's actually, yeah, that's equal to the integral, and that's equal to 1. Integral from 0 to pi of tangent x. This one you have to be a little bit careful. This one you can't really apply the fundamental theorem directly here. There's probably, you could maybe use limits to evaluate this, but if you remember the graph of the tangent, tangent is undefined at pi over 2. So we have we're going to have vertical asymptotes at pi over 2 and minus pi over 2. So pi is right here, and so the function is undefined at pi over 2, so it's not continuous. So this fundamental theorem of calculus says that f has to be continuous, so it says if a function f of x is continuous on a closed interval a to b, and if the function capital F is an antiderivative. So so this one, there might be a way of evaluating this, but we're not going to try to do that here. You can't apply the fundamental theorem. So the tangent x is not continuous at pi over 2, so you can't apply the second fundamental theorem of calculus to evaluate that integral. Okay. Okay, so here's a proof of the second part of the fundamental theorem of calculus. Let's we have a partition x0, x1, etc. up to xn of the interval a to b, and x0 would correspond to a, and xn would correspond to b. And we can write f of b minus f of a, capital F of b minus f of a, as the summation I equal 1 to n of xi minus f of xi minus f of xi minus 1. So we're just splitting this into n different subintervals, and we can apply the mean value theorem. The mean value theorem says that the derivative that the on each subinterval that's f of x minus f of xi minus f of xi minus 1 is equal to f prime of ci for some ci times the quantity xi minus 1. So this xi minus xi minus 1 is just delta x, and then if we take the limit, and ci is just some point on that interval, and if we take the limit, we get the definite integral from a to b of f of x dx. And that concludes this presentation.